Good afternoon. My name is Victoria Sheehan, and I am the Executive Director of the Transportation Research Board. Prior to serving in this role, I was Commissioner for the New Hampshire Department of Transportation, and I was also a member of the American Association of State Highway and Transportation Officials, or AASHTO. Back in October of 2022, it was announced that I would be joining TRB, and that week I happened to be attending an AASHTO meeting. Secretary Pete Buttigieg was speaking that week and also graciously sat down with a group of state DOT CEOs. Knowing that I would be transitioning into this new role, I took the opportunity to ask the Secretary what he personally considered to be the highest transportation research priorities. Of course, he talked about safety, electrification, and climate, as well as equity, topics that are covered in the US DOT Strategic Plan for Research, Development, and Technology. But he also mentioned the need to continue doing other types of research. Each and every day, transportation professionals work to stretch the value of the investments that we're making in the transportation systems. Continuing to advance materials that last longer, so that assets require less maintenance, and advancing greener materials are priorities that we share here in the TRB research community. And we have a number of standing committees and subcommittees who are tackling these issues. At other sessions this week, we've showcased the work of TRB and others in this arena, but we were delighted to hear that the Secretary himself had requested that we include the session today entitled New Materials for Infrastructure, Reinventing the Roadway, Runway, and Railway. This is the last of 7 sessions that US DOT organized this week, so we thank the Secretary and his team for his support of TRB and for being here with us today, both for the Chair's plenary and for this session. We have a great working relationship with US DOT and all of our federal partners, but we especially appreciate the close partnership that we have with Dr. Robert Hampshire and his team. Dr. Hampshire is Deputy Assistant Secretary for Research and Technology, and he will be moderating today's session. So at this point, I'd like you to join me in welcoming both the Secretary and Dr. Hampshire. I know it's going to be a great conversation this afternoon.
Hey, good afternoon. And thank you very much. Thank you, Victoria, for your outstanding work and partnership and leadership, and for acknowledging our team. Thank you, Dr. Hampshire, my colleague who leads a terrific team of researchers and helps to guide some of the work we're doing in partnership with so many of you and so many educational institutions around the country. I really do love talking about pavement. And I know I'm finally in a room where it's safe to acknowledge that pavement durability is one of my love languages. If there's any place in the world that I can talk about this, it's here. There are so many exciting things going on in transportation technology and innovation and within the scope of what TRB thinks about. Flying cars, ammonia-powered ships, the Internet of Things. But pavement and material durability and sustainability, I think, is one of the most extraordinary and underappreciated dimensions of the things that we work on in transportation. As you might imagine, my view on this is largely shaped by my time as mayor. I remember as I took my part in the enduring battle, the predator-prey relationship of mayor versus pothole, asking our public works director, what would it take to just resurface the whole city, just every lane mile of road we got? Suppose we did that. With the funding that we have, how often could we do that? And he did some napkin math and said about 75 to 100 years. Then I asked him how long it would last. And he said, well, with our freeze-thaw cycle in our part of the Midwest, somewhere between 9 and 12. And I thought, what I would give for even just a 13th or 14th year of durability. Because I thought about what we could do with those limited dollars. And that same thought has followed me now to, of course, a radically different scale. as we contemplate the proportions of President Biden's infrastructure law that is putting $1 trillion through the American economy to enhance the transportation and internet and water and other infrastructure that we all rely on. Because if you can take $1 trillion, or let's just say the roughly between 100 and 200 billion dollars that's going into roads and bridges out of that, and make it 1% more efficient, right there you've unlocked $1 or $2 billion, which isn't just numbers on a page. That's bridges or roads that won't be built unless you can find those efficiencies. And that's just the durability piece. There's so many other pieces that go with this. So I'm not talking about this in terms of science and innovation for the purpose of science and innovation, for this is a nerdy pursuit. We're about steering innovation toward the public good, and the public good is very much at stake here. Whether it's helping to save lives on our roads, whether it's protecting our communities from the most extreme impacts of climate change, everything that can make our infrastructure more effective, more efficient, more resilient, and longer lasting than ever before deserves a great deal of attention. Last October, I had a chance to see some of our own work on this at Federal Highway Administration's Turner Fairbank Highway Research Center in McLean, Virginia. I saw their new pavement testing facility. That facility can collect performance measures through about 300 embedded sensors and about 7,500 load passes that are applied every day at heat up to 140 degrees Fahrenheit, creating an incredibly rich data set that will help develop new standards for better pavement that can last longer, even capture carbon, and in a vision that sounds outlandish, but I know many of you see how it's within our reach, potentially even help to heal itself. And that's just the pavement. Many of you and many of our panelists are involved in ways that might revolutionize the way that steel or cement are produced, just to take a couple more examples. And with the right kind of investment from the public, private, and academic sectors, I really think that we can not just rebuild our infrastructure, but redefine how it's built. Here's another way to think about it. 60 or 70 years separate the flight at Kitty Hawk from the moon landing. But the materials that we depend on for our roads, our sidewalks, our bridges, in my opinion, have more in common than they should from those that were in use at the time of the Roman Empire. We're changing that. You're changing that in ways that I think deserve more attention, which is why I wanted to be sure to be here, to learn and to highlight how this research agenda could have an outsized impact on us in our time as we're undertaking perhaps the biggest rebuilding of U.S. infrastructure in our lifetimes. So with that, I'll end my monologue and listen to the real experts, but thank you again for the chance to join you.
Thank you, Secretary Buttigieg. My name is Robert Hampshire. As you see, I'm the Deputy Assistant Secretary and Chief Science Officer for the department and lead the Office of Research and Technology. Again, it's always just a true pleasure to be here with you at TRB. As many of you know, I'm a product of TRB, and this conference always is energizing, and hopefully this panel takes the energy to another level. At this time, please, panelists, please join us on the stage. As they're walking up, I just want to sort of set the stage and reiterate a little bit what the Secretary mentioned about how these materials are really underlie the foundations of our infrastructure, be it steel, concrete, asphalt. You know, certainly those things have been done the same for almost 100 years. But we're at the onset of innovation, true innovation to help to solve the problems that this nation, and in fact this world, must tackle. And so it's just really exciting to have the panelists here today. I'll just kind of go through their names here shortly. The way we'll do this is we'll have the moderated Q&A here first for about another half hour or so, and then we'll move to the next part of the program, which are going to be individual presentations by our experts. But who we have here today goes from the early stage innovation. Matt Pava, who's a program director at DARPA. Matt, if you would raise your hand. Franz Joseph Alm, a faculty member at Massachusetts Institute of Technology. He can tell us a bit more about in-ground charging, inductive materials, and much more. As we move towards from pure research into development and scaling, you'll hear certainly from Tadeo Carneiro from Boston Metal. They're developing a way to create steel with no carbon consumed in the process of making that steel. Thank you for being here. All the way through the development and design with Maggie Kwan from AECon, who's really done so much on vertical construction, meaning buildings and skyscrapers and towers in New York City and everywhere around the world. Maggie's imprint are on those buildings. There's a lot to learn from those folks. And we're rounded out with Mo Jamshidi, who's not a stranger to this audience, from Nebraska Department of Transportation, very active in AASHTO about the standards, the testing, how to actually procure these materials. And so I really look forward to this conversation, and I'll move over now to my moderator seat there next to the secretary. We'll get started. All right, good, you can hear me. So I'll start this off with certainly, Mr. Secretary, turning to you. You mentioned a bit about what the department is doing as it relates to new innovative materials, durable materials. I know you visited federal highways. There's so much work that's been done in our department and in this industry, federal highways colleagues, FAA. Can you just say expand a little bit more about what you see the role of DOT is in the development and deploying of some of these materials?
Well, I think our role really is to make sure that we're, first of all, of course, to the extent we can, directly supporting research that's making a positive difference. Your team, our UTC relationships, and so many others that we have. Second, to make sure that a good understanding of the role of materials is encoded into the decisions that we make. After all, we have so many different kinds of considerations that we ask project sponsors to think about. Incentives that we shape for project sponsors, and these should very much be among them. If on behalf of Uncle Sam we're buying what adds up to hundreds of billions of dollars in materials, we have a surprisingly low level of traditional attention to what those materials actually are. And if even a marginal change in the sustainability, durability, or quality of those materials is possible, that could be massive if you multiply it out across all of the things we fund. The third thing I would mention, and especially because we're here, is helping to cross-pollinate those best practices. So often I found that some problem that people in one part of the country are scratching their heads about has actually been solved in a very different context by people somewhere else. TRB is one of the bodies that is exquisitely effective at creating those connections. I think we have a responsibility, because we touch so many different parts of the transportation world, to do the same. So all of those, I think, are a role that we are enthusiastic about playing. The sense of urgency we feel about doing so is multiplied by the fact that we have this now once-in-a-lifetime infrastructure investment on our hands. We want to make the absolute most of it to lead to what I hope will be a step change in some of these things that are being worked on in the research world today.
Yeah. I think that's the panel here today. We'll ask them here in a second as well about what are some things that we as a DOT and the government more broadly could do. Some of those, be it incentives, guidelines, advanced commitments to procure some of these materials. I know the infrastructure bill certainly has new programs that certainly incentivize low embodied carbon materials, for example. But I kind of want to start a little bit on the innovation, early in the innovation pipeline, and hear from really dynamic Matt Pava in terms of the types of things that DARPA and the Defense Department is doing around advanced materials. I don't know, Matt, what are some of the things, as you're thinking about your programs, that us at USDOT and others can do to support or further those efforts?
Right, thank you. As Robert mentioned, my name is Matthew Pava. I'm a program manager in the Biological Technologies Office at DARPA. I manage a program called Bio-Inspired Restoration of Aged Concrete Edifices, or BRACE. I'll talk about that in a minute. And Robert, what we're trying to do on BRACE is to ask the question of whether or not it's possible to develop technologies that harness or are inspired by some aspects of biology to impart the ability for existing aged concrete structures to repair themselves. So can I take a technology that I can apply to the infrastructure that I have today such that I can extend the serviceability of that infrastructure? You have to recapitalize less frequently.
Can you say, what does that actually mean? Like, what's a biological kind of approach? Like, what is it? What are you really doing?
Some previous work that DARPA has sponsored on another program that since concluded called the Engineered Living Materials Program demonstrated it's possible to produce bioconcretes. So biological organisms will precipitate minerals like calcite. And those are useful building materials. And you can glue together different materials like sand, for instance, to make pavement surfaces and such. On BRACE, we wanted to ask the question of saying, like, okay, it's interesting that we can develop new novel materials with biology, but can I take biology and apply it to a material that's traditionally viewed as abiotic and harness some of that capability so I can fill in voids and cracks that might have developed in that structure over time?
Yeah. I mean, when I first heard about this, like, genetically engineered bacteria that could then eat something and create limestone, I mean, that's just amazing. You know, and I think when we look at Mo's face here, he's like, oh my gosh, when you think about implementing something like that, we'll come back to what does it take to go from the lab to the road. But, you know, as we think more about this sort of earlier scale, and feel free to jump in if you want.
Just that it seems so far out, and yet, I mean, the idea that the excrement of a microorganism could be the solution to an infrastructure problem seems wild. but some of these principles that are, you know, we're hundreds of years into harnessing in fields like pharmaceuticals, for example, that could be applied to now at a different scale and for two different problem set is incredibly compelling.
Yeah, and that could put us into the biomanufacturing conversation, but there's a lot there. But maybe turn to Franz here at MIT, and again, we're earlier in the innovation cycle at MIT. Can you say a bit, Franz, about what you would kind of support or things that the federal government, for example, could do to further your kind of work?
I don't want to take the microphone, but I think you wanted to talk to me about it, right? So I believe my love for pavements and materials goes one step further in the sense of that I believe that infrastructure is the key to achieving the energy transition. And classically, roads cannot do that, right? You know, they're just one thing. They're there for ensuring mobility and avoiding that secretary sleeps badly because of potholes, right? So, but imagine that you could actually store energy into each pavement structure. Theoretically, you would say, no, it's not possible. Come on, we cannot put batteries in there. But if you just add a little bit of carbon black into, mix it up with cement, then the magic of chemistry takes place and makes out of it an electron conductive material. And what you can then do is you can store energy in the system. So what we are right now working on is the dream or the nightmare of everybody who has an electric vehicle to charge your car while you drive. On the same road, made with the same way as it is done right now, mixed with concrete, in a way that everybody has access to this energy source and the investment of the federal government through our pavement structure for mobility.
Yeah, thanks, Franz. I think you know, part of that sort of inductive charging, part of the things that you all are doing is really leading the way. We have, you know, some of our UTCs, University Transportation Centers, are also taking on that challenge, and so there's a good example of something that's really out of the lab and starting to move into practice. In fact, in Michigan, a few weeks ago, I think the first quarter mile of sort of inductive road went online. So these things are getting closer. We're going from the lab all the way to closer to the road, and it's just really exciting. I don't know if you had any additional piece there, but okay. And so today, you know, I think, thank you, Franz. So now we're going to move a bit closer to this implementation and, you know, from research to development. and actually in practice. So Tadeo at Boston Metal, as we think about, particularly making steel that doesn't require carbon in the processing. Can you just say a little bit first about that? That's fascinating. But then what are some of the things that, again, I'll give you that same question that from the federal government or DOT's perspective that you might recommend for us?
Sure. Steel, since millennia, since the Iron Age, for each ton of steel, you emit 2 tons of CO2. So if it is, and today we are manufacturing 2 billion tons of steel every year. So steel manufacturing alone is responsible for 10% of all the CO2 emitted in the world. So what we are doing is we are developing a technology that will eliminate that completely. So by making Faraday's dream a reality, we are going to use electricity, green electricity, to manufacture steel. And we can use in the process the same technology to extract value from mining waste. So that's another environmental issue that our technology can solve. So very excited with the prospects.
Yeah, thank you, Tadeo. I think I would love to see the processing in person. I think you guys even made in America here up in Boston area. So it's just really great to see that kind of innovation, true innovation, something that's new and useful, hitting the ground running. And just transition a bit to Cooper, from the breakthrough energy, you all invest in these kind of technologies, meaning that you see the real value, you see the mission, but also you all probably see a future here for scaling. Can you just maybe say a little bit about what goes into you all's decisions and investment in this space?
Yeah, absolutely. Before the panel, I was wishing for anonymity, and it went a little bit too far. But no, so I represent Breakthrough Energy Ventures, and we were really formed in response to the Paris Climate Accord. As a private sector response to the public sector commitments being made in R&D to decarbonize the global economy. And so we take a very systems view, but that's very market-centric. And so our basic theory of change involves the pillars of technology, finance, policy, and behavior change all aligning. And our organization in particular likes to focus on solutions that have the potential to mitigate on the order of 1% of global greenhouse gas emissions, or 500 million tons per year. So that sets a really grandiose scale. And when we think about grandiose scale, there's nothing that's more relevant than infrastructure, and in particular the materials that go into infrastructure. This is my personal favorite part of the whole of the decarbonization story, because it is the most challenging and recalcitrant to change. But I'll also just point out a note of potential vision, which is that these are precisely the materials that if we remove the carbon, it's the only materials we use enough of, that they could be the place that we actually store carbon. A vision of our infrastructure future, which is carbon negative, is the only vision of a place that we can actually have true carbon negatively scaled. And a few of the technologies that are represented by this panel and some others that we can talk about make that potential vision reality. And I'll just comment to your question about the role of government and the role of the DOT specifically. Steel and cement are the most dominantly scaled merchant markets on the planet. And the way that we need to pull forward innovation is by being able to provide a clear path to profitability and scalability. And the financing strategy around that is really challenging in merchant markets. Advanced procurement from the most important customer on the planet, the DOT, is the single most impactful thing that we could imagine for enabling a financing pathway for novel material systems and novel strategies for making the same materials that we use today, but with lower carbon. So the government has an absolutely crucial role to play, both in navigating the regulatory frameworks and the standards, but also in directly being the demand signal to help bring these materials forward. So thank you for the interest.
Yeah, and thank you for that. I think understanding more of that business case, really for innovators early in the pipeline, you may or not think about the business case, but we got to connect these parts of the pipeline together to really then accelerate through that pipeline. I think this is really important, and one of the roles of this panel.
Let me put an exclamation point on that, because I think there is an area of research just as important in the economic space about what stands between us and the adoption of some of the more proven materials. And again, I think if you think back to the mentality of a mayor confronted with a 75-year backlog in paving potholes, it means that often an elected or appointed leader in that situation, when presented a chance to have, let's say, a 40% better durability at a 20% price premium would have to say no, which on its face is by definition irrational, but in the circumstances is inevitable because there is so much pressure just to catch up on the problem, the piece of the problem that's in front of you. And I wonder, since you're very attentive to that side of the equation, what insights you've found that might help point to how, either on the terms you just mentioned or in other parts of the marketplace, those economic problems can be socialized and solved.
Absolutely. I think it's utterly crucial. I think at the end of the day, we'd all love to believe that we could make perfectly rational choices in all moments, integrated over the future, and decarbonization would be a clear story. We don't make those choices today. And the reason is that the incentive structures that we're all in, whether you're an elected official or whether you're just in the private sector making a bottom line decision, is you need to have the incentive alignment. And so we really focus on the belief that the scalability of solutions is utterly dependent upon a profit incentive within the market boundary conditions, which are a function of policy. And this is one of the key functions of policy, such that your issue was that you couldn't make a valid return decision in the context of the tenure of the mayorship, right? And I think that if the boundary conditions were otherwise, or if the technology solution or innovation pathways were available to make that a reduced cost opportunity for you, given all in, that's the incentive alignment that we absolutely require. So our particular organization is focused on that alignment of policy incentives, but really about innovation in the private sector to as deployed from public sector funds, to enable the moment-to-moment decisions of every individual actor be one of selfish acting, of what is actually appropriately aligned with your incentive. And I think that we cannot ignore the role that cost plays. And we also cannot ignore the role that in infrastructure specifically, and maybe uniquely, risk plays when we're talking about the literal foundations of our society. So there's another role of the government here, and thank goodness Mo's here, of helping us define what are the materials that are safe, that we can feel confident are not a political risk or an economic risk to choose, because they are entirely proven and understood, and we feel comfortable building our bridges and roads out of them.
Yeah, those points are just such so on point. Particularly, we go back to Mo, and I'm sort of teeing you up a little bit here later that like these incentives to make the decisions, but when it comes down to the procurement decision, you've made certainly as a mayor those kind of decisions, but how do we think about de-risking those decisions so that things actually get built in an economical way? And so we're getting to you, Mo, but we'll first go to Maggie, because the vertical sector, buildings, skyscrapers, and the vertical sector, I think, is a bit ahead of the so-called horizontal sector. You taught me that, Maggie, about the infrastructure you call horizontal and buildings are vertical. But can you just say a little bit about the state of this discussion inside of buildings and vertical construction?
It does have a little difference because high-rise building, some of you might be coming from New York City, so you might know some of the major cities like Chicago, LA, they all have high-rise building. One of my slides later has shown the tallest Western Hemisphere is, I have to say Freedom Tower, AKA World Trade Center 1. And because of the height, it's 1,000 feet tall and above, the mixed design is a little bit different than horizontal, which is roadway, bridges, and tunnel. The strength is different, and the deflection is a little bit different. So we've been doing that, and we've been studying and collect data since early 2000s. Some of you might know, because you all specialists in this room, some of these material is not new. It just matter, did we have time to discover them, collect them, review them? Yeah. And that's where we are. We've been doing this right now in 12,000 PSI, 14,000 PSI, 16,000 PSI concrete design mix. That's for high rise. And horizontal, which is usually about 4, 5, 6,000 PSI. That's the difference between roadways and bridges and high rise. We might be in the near future keep going. It just we find a little equation, I call them. We use the material from landfills. We place some of the cement. We need to recalculate these equations to come up with a better solution, like what the Secretary said before. And this concrete is coming from Roman. The recipe seems so old, but look what we've been eating. Now we have gluten-free and all kind, food. Why are we not thinking about what we have right now? Yes, we need scientists keep moving forward, but we got to look at what we have. We got landfills. We got all these waste. We could use them, and now not only we could gain our constructions, our society, but it helps the planet. It's a win-win-win situation. And on top of it, it might not cost a lot. And that's where the balancing act is part of what everybody should think about it. Technology is great, but also you got to balance economics. Unless someone said, money is no object, then, we could go to a lot of places. But everything should have a balance. Cannot be tipped to one side more than the other. And some of us need to do that. Others need to help us to keep advance. And some just stay where we are for now. And that's where the difference between high-rise building, it just, we have recycled steel. And on top of it, there's I know in this room, you guys use ASTO. We use a lot of different codes. And one of the things that we also use for over 20 years, LEED, as environmental on a high-rise building. We have recycled material for windows and everything else. So in a way, in building size, recycled material is not just now. We've been doing it. Slowly but surely, but we're there. And now we want to partner with our transportation side to bring them to a place that is not that scary. We could do it. We had all these genius here. We couldn't figure it out, then I don't know what country can figure it out.
So that's a great perspective. I think a lot of the things that you mentioned are closer to the boat than some of the other pieces that we've talked about. Recycled materials, recycled pavements, be it pavement, asphalt, steel. And so I think you said maybe it's not that scary. Those things have maybe been de-risked, and in the vertical sector, really have a good head start and a lot for us to learn from. I don't know.
The only thing I would editorialize is, of course, in the buildings world, you've not only identified some physical engineering and material solutions that might have applicability in infrastructure, but also some of the financing solutions along the lines of what Cooper was mentioning, right? If you're in the world of managing buildings, then you're very familiar with energy savings contracts, for example, that took on that exact question, right, of how to make sure that whoever's making the decision about what energy technology to use was dealt in on the long-term savings and shared the savings with the vendor in ways that I just don't think have fully reached the markets for some of the materials procurement and engineering that happen in the horizontal space. So it's not just engineering innovation, but I think in some ways finance innovation that you also might be able to share with us in the horizontal world.
Absolutely. I mean, one of the things that we have later on, I also represent Concrete Industry Board of New York City, which is ACI chapters. And I'm the president, and we have a committee come up with a guideline. It's called Green Concrete Guideline. It really lays out how we use step by step the specification that came from Port Authority. Honestly, we have a committee come with private sector and public sector. It's one of very unique committee together. Put our brain together. We want to give back. Let me just clarify. We all volunteer and we want to give back. We want to give back to our city, our state, and we want to share with others, state and city. And the thing is, we have a solutions. We know what we can do. We already, one of my example later, is show that we actually cut down 50% of cement. But the Port Authority are demanding use inventory in their project. So private sector is using it, public sector also using it. And the thing is, can we share with the rest of the state and the country? It's up to everybody. Everyone, every city and state is unique. You can't use one, one size doesn't fit all. You have to pick and choose what makes sense, what balance. And one of the low carbon, might be good for environment, might not be good for a project. So you also have to balance all this. Yeah. And on top of it, as a client, some client is, well, I got to be careful about that one. Because some is more focused on certain thing than the other. But we all want to do the best we can and do our job. So we want to build and complete the best project we can. Yeah. And that's what it is. And you have to find a way to share. Yep. And that's what I'm here, and I'm honored to be here. Would like to share what our finding as a committee, that we're doing it, is working. And hopefully you guys can learn, or you want to use it or share, and we're happy to help.
I mean, that's a great message for this audience, and you're coming as sort of an emissary from the vertical sector to really share some of the great news that you all have done and the lessons learned. The audience here, I'm looking at the various committees here at TRB and researchers who have worked on these materials for many years, refining them, de-risking them, getting them ready to put into service. And so let me just turn to Mo to kind of round us out, and I'm kind of looking at the clock a little bit too, but give Mo a chance to kind of round us out, and your perspective from really, you've spent so much time thinking about de-risking, procuring, how to actually get some of these things in the road. So, please.
Yeah, I've worked for the DOT for 40 years and been in many roads, bridges, pavements, mostly materials engineer, and I chair the materials and pavement. And for a minute, you all can probably see a day in my life. I got two guys on my left. One of them wants to put living things in the concrete, the other wants to electrocute it. And I have to write a specification that makes sure the contractor meets both of those requirements and still have a pavement that doesn't have potholes in it. So our challenge is to take all of this good work and put it to practice. And the week that we've been here so far in the country, there's been millions of tons of asphalt put in the ground already. So despite what most of people think, we're still building things like the past. Asphalt is black and concrete is white. In the last 20 years, we've made a lot of progress to making them more sustainable and making them last longer, and therefore we don't have to go out there and replace them all the time. One of the things that is critical is to realize we're still making pavement. Pavement, both asphalt and concrete, are the majority of the things we do in the transportation. Yes, we build bridges and rebars and all that other stuff, but the main thing is, as you said, Secretary, is that pavement. And if we can make it last 1 year more, we save a lot of money that can we spend other places. And that's what goes through a materials engineer at the DOT. How can I make that material last longer? DOT is really open to innovation, but it has to be scalable, it has to be practical, and it has to be safe. And it can't be something that it's not really thought through about what the DOTs need. But when we find something, we use it, and we use it very effectively. Let me give you an example quick. Warm mix asphalt. In 2008, we hadn't even heard of warm mix asphalt. I was fortunate enough to be a group of 15 of us went over to Europe and learned how they did it because they were ahead of us a little bit. In 2009, in my specification, I required it because it was a great spec that can reduce the asphalt temperature by 10, 20, 30, 40 degrees which now I don't have to burn as much fuel and I can deliver it farther. So when good things happen, the use of wrap, we started at 10% recycled asphalt in our pavement just 7, 8 years ago. Nationally, we're up to 20%. In Nebraska, we use 50%. In fact, we incentivize the contractors. We give them a big part of the money if they can show us they can put 20, 30 and more, because they have part of the savings. And what does that do is it gets rid of all the old asphalt into the new, and I don't have to go back in the mine and get the aggregates and the oil. So we're ready to go to work. You guys bring the material to us, but do understand what we do, and we will work with all of you and to make it happen.
Mo, I think that's really a great place to kind of start to wrap this portion of the panel. Really, how to really give credit. You're a representative of many folks in this audience, all the great work that has happened over the years, and really look forward to you all leading those changes into the future. As we close, Mr. Secretary, I'm going to give you a chance to kind of close us out here on this panel.
Well, thank you. Dr. Hampshire, I envy you being able to stay here and geek out a little bit more as they get the hook for me, but I want to thank and recognize each of our panelists, and again, just emphasize the importance of paying attention to some of these things that are literally under our noses that represent just as important a dimension of the opportunity in front of us as some of the things that capture a little more attention because they move. And yet so much of what we're investing in terms of its intelligence, its durability, its sustainability, is what we move on or around. And I know that I'm very literally preaching to the choir in this regard. So more than anything, I just want to urge you to continue this good work, offer up our continued attention to this in the policy space at the federal level, and invite this community of practice to continue to wow us with the ideas that you are coming up with, be they the engineering and scientific advancements or the policy and economic advancements that are needed to actually unlock their value and their potential, because it really is, in the grand scheme of things, not just money saving, but life saving. So I will leave you to the continued discussion, but honored again to be able to be here, and just don't let anybody tell you that materials aren't glamorous. I think they are. So thanks very much.
Thank you, Mr. Secretary. Incredibly energizing. Like I said, I knew we would bring the energy level up with having the Secretary's leadership and participation on the panel. Just really, really fantastic. We're now going to move to the part of the panel where we're going to have our esteemed panelists provide a little bit more background on some of their work, but a little bit deeper dive on this perspectives that they're coming from. And so I believe first we have Matthew Pava from DARPA, who's going to provide, and these are about 5 to 7 minutes to kind of go into a bit more background in the next portion of the program here before we ultimately close. So with that, Matt, please.
Great, thank you. So I'm Matthew Pava again, Program Manager in the Biological Technologies Office at DARPA. Before I get started, Robert and Chris, thank you very much for the invitation to participate in this panel. It's really nice to see the breadth of work spanning from basic science all the way up to things that are much more applied. So I manage a program called the Bio-Inspired Restoration of Aged Concrete Edifices, or BRACE. So concrete, I think we can all agree, is a fundamental material and part of our built environment. It is susceptible to deterioration, of course, and climate change can be a factor in that deterioration. Concrete also is not particularly friendly to the environment with respect to CO2 emissions. So the fundamental question that we're trying to ask on Brace is whether or not we can develop technologies that can be applied to our existing infrastructure that'll extend its serviceability, so we have to recapitalize that infrastructure less frequently. So DARPA, the D in DARPA, standing for defense, we are concerned with national security. Military, the DoD, relies on concrete infrastructure, not dissimilarly from the civilian space, with respect to its mission and operations. There are some kind of unique architectures in the DoD that you might not find easy analogs to in the civilian space, but the concrete is relatively similar. So things like missile silos and a variety of shoreside infrastructure actually date from largely the early to middle part of the 20th century. So they're at, or in some cases, exceeding their design service life. It's not really practical for us to recapitalize wholesale all of this infrastructure, in part due to just how much infrastructure that we've acquired over the past century plus relative to our ability to emplace new structures made out of concrete. It would take quite a long time to do that. So there are some various mechanisms, obviously, that contribute to concrete deterioration. Cracking and corrosion are two of the most common, and they collaborate with one another to foment deterioration in our structures. What we want to do on Brace is to develop a technology that is relatively easy to apply to those existing structures to maintain a prolonged capability for ongoing repair of cracks, the ability to monitor that process as it's taking place, and understand how it is impacting a structure to which it's applied, such that we can quantify where it's working, the extent to which it's working, and if there are any places in a structure where it might not be working, so we can alert facilities managers or civil engineers to take additional remediation steps. So again, regarding the DoD use cases, as we were constructing this program, we were mindful of two timescales upon which we might consider repair. So one timescale probably looks very, very similar to problems that this audience is familiar with respect to what we call a strategic timescale. So this is a relatively slow deterioration process measured on the order of years to decades. And in this, we're concerned with structural concrete. On the other hand, there is a somewhat unique to the DoD use case where we might have a structure, perhaps an airfield that's in a far-flung location, and managing the logistics to actually implement a repair, moving the people, the materials, and the equipment necessary to do a repair is very, very challenging. But we might need to make repairs on a very short timeline. So this devolves into sort of a cheap, quick, and good optimization, if you will. I need to make a hasty repair. I don't have a lot of resources to do it. And what often suffers is the goodness or the durability of that repair. So it would be nice if we had, in those circumstances, technologies that could overlay onto that process that would allow us to extend the durability of that repair made in those circumstances. So there's a few technologies that we might think about when we're talking about extending the durability of concrete. One of those is some technology that DARPA played a part in funding via the Engineered Living Materials program. So things like self-healing concretes or engineered living materials offer us the promise of structures that are built out of them that can repair themselves when cracks emerge. Unfortunately, most of our infrastructure is not built this way. So this really doesn't apply to this challenge of aging infrastructure that we have. There's sprays and other topical applications which can biomineralize, they can fill up cracks, but the degree to which they can penetrate the depth of a potentially very large section of concrete is limited, and they tend to be one-time applications. So you apply it. If that repair fails, then you have to come back and retreat. If another defect emerges, then you have to come back and retreat. And what we wanted to do on Brace was to develop a technology that could check all of these boxes. So biology offered us a little bit of inspiration in terms of how this might occur. So fundamentally speaking, we're talking at some level of a mass transport challenge. I have material that I need to implement a repair, and I need to get it into potentially some depth within a large concrete segment. How do I do that? So biological structures afford us an example here with vascular systems. So vascular systems transport nutrients and other materials throughout the bulk of an organism. And we obviously are pretty familiar with an example that resides within us in terms of our cardiovascular system, but there's other examples from nature that perhaps are more germane to the problem at hand. So things like filamentous fungi that participate in ecosystems. Think about large forests, for instance. And they'll create dense vascular-like structures through media like soil, and they can transport materials quite some distance from a source to a sink in that environment. So the question was, could we impart a vascular-like structure into the cracked, porous nature of deteriorating concrete to facilitate repair? And this is how we structured the program. This was the fundamental ask.
2 minutes.
Got it. Okay. This was the fundamental ask when we released the solicitation for proposals. So we divided this program into 2 different technical areas. I'm just going to give a super brief overview of what those are. The first was engineering the vascularizing effector. This is essentially the thing that's going to vascularize the concrete. It'll fill up cracks in that concrete, and it affords us the opportunity to monitor its presence and functionality over time. The second technical area complements this. It's the set of technologies that you need to actually use this thing. This is how do you apply it, how do you maintain its function over time, and then how do you test material that's been vascularized, particularly across increasing length scales. And then finally, if I've applied this to a structure, I've changed some fundamental material property, can I predict how that structure is going to perform over time? So as is typical for DARPA programs, we regularly interact with a variety of transition partners in the DoD civil engineering community, but as concrete is not a unique to the DoD problem, of course, across government to include the Department of Transportation. Another aspect of our programs that's quite common is to try to consider the ethical, legal, and societal implications of new technologies that we're developing. And if we're successful in the risky endeavors that we fund, what might that actually mean on the back end of a program? So we have an LC group that informs the program management team of what some of those issues might look like if we're successful. And with that, I'll conclude and yield the floor to the next speaker. Thank you.
Thank you, Matt. I think we thought it was very important to have this DARPA presentation, particularly for this community. There's an open program, there's funding, there's partnership opportunities, and so just a great opportunity for this audience. Thank you. Let's move now to Franz, please.
Thank you very much for having me. In the next minutes, I'm going to share with you that my deep belief that our national infrastructure is the key for reducing, 1, the environmental footprint of our mobility, and 2, to have a competitive transition from fossil fuel-based energy economy. Specifically, I want to convince that the technology is already ready in the labs to create energy-storing solar-powered buildings, structural frameworks for offshore wind projects, and eventually, and that's not completely ready, but in the making, self-charging roads for electric vehicles. So why do we care about this? First of all, you know that the difference between fossil fuel and electrical energy is that fossil fuels has identity of energy source and carrier, whereas we have always the imbalance between energy harvesting and energy consumption for renewable energies, which is why we need to find something differently. On the other hand, we have a material, concrete, which is a fantastic material, but it has its environmental footprint, and the industry is committed to reaching carbon neutrality by 2050. But how can you achieve this? That we are going to hear about replacement solution, but the true solution actually is if you add another function to the material. And that's what I want to show you. So concrete cannot store electricity unless you add something to it. And that what you have to add to it is charcoal, actually to be more precise, carbon black. So when you mix carbon black with cement and add some water to it with some superplasticizer, what you then obtain is an electron-conductive carbon cement composite. And I invite you to take your coffee mixer or your coffee grinder, actually, just put cement ratio 1 to 10, so 10 cement, 1 carbon black, mix it, put water, and you have an electron-conductive material. Well, what happens then is, once you have electron conductivity, is the following. Actually, it's magic of chemistry which takes place, that when you put carbon black with water, the material clumps. You know this all from cooking, from that clumps. But then when the same water is consumed by the hydration reaction of cement, boom, you get a percolated volumetric wire through the system. What can you do with it? Well, the first thing what you can do is, for instance, get rid of the salt on your roads, durability, just connect it like a stove to it, and what you then see is you can basically monitor the temperature exactly of your pavement. These are mortar slabs made of this material. And the second one is, of course, the energy storage. And why should we care here as a nation, not only as engineers? We should care because when you look where right now the battery technology is produced, you will realize that the US is losing its competitiveness unless you change the precursors, and here, cement and carbon black. Then we stay competitive. So how does the technology work? Very easy. You have a pore space in your material. It is filled with electrolyte, a salt solution. When you then charge your volumetric wire, what then happens is that the counter ions actually come to this volumetric wire and hang on it. This is not a battery. This is supercapacitor technology. But it works. You have no limit in terms of cycles, etc. Here's a typical example of a small one, how it looks like. So one single one. Don't worry about electrocution, right? Don't worry. We only operated 1 volt for each one of those supercapacitors, so don't worry about that, right? But you know, then you hang them, you build them up in series, and what you then obtain, you basically have a storage medium. Every wall can be a energy storage solution. You know, typically, just to give you an idea, you need roughly 45 cubic yards of concrete for a building, for a normal house, for a normal dwelling. But the high-end application is, of course, you start then building them up a little bit like Oreos, fill all the columns up with it, and you have then energy storage. Well, as much concrete you build into your structure. Finally, you can then scale this, of course, up, and then you come here to the high-end application. And the high-end application, I will end there, is electromagnetic induction. The idea basically is that you have inside your pavement, now that it's electron conductive, an electric field. You have an electric field in your electric vehicle, and if this frequency is high enough, and it's still an if because I haven't proven it yet, you can transfer this energy from the pavement up there. And for anybody who has an electric vehicle, we wouldn't be scared to find a charging station. With this, I thank you very much for the honor of being with you.
Thank you. I think very exciting. I think we could spend so much time on that, but unfortunately we don't have enough time here. But we'll now turn to Dale from Boston Metal.
Good afternoon, everyone. Thanks for having me. It's a pleasure to be here to present what we are doing in a new way to manufacture metals. So it's So 10% of all the CO2 comes from steel manufacturing today. What we are developing is a technology to eliminate that CO2 emissions from steel manufacturing. So it's a millennium problem. Since the Iron Age, 1200 BC, you emit CO2 when you need steel. And so we are eliminating that problem by substituting the carbon in the equation for electrons. So even if you find 1 billion tons of scrap to remelt, you still need 1.5 billion tons coming from iron ore. And that's where the problem is. All the steel industry is pledging to be carbon neutral by 2050. If this is to happen, you have to phase out all the blast furnaces by mid-30s. And then our technology would be scalable to millions of tons as needed. So how does it work? let's see if I can make this run here. Yeah, so it's an electrolytic cell. You keep adding iron ore in the cell in a soup of oxides, which is the electrolyte in the cell. And you pass electricity. What happens is the electron will heat everything, make everything liquid, and also will split the bonds of the least stable oxide. So you design that soup to have the iron ore being the least stable. So you collect your iron in the bottom of the cell, and you emit oxygen. So that's basically what the technology does. The cathode in the cell is the iron that you produce itself. The anode is a chrome-based alloy that we call it inert anode because it doesn't participate in the reaction. You passivate as you form oxygen, passing the electricity there, as described, and you continue to pass electricity and produce your steel. Once you collect enough metal in the bottom of the cell, you tap the cell, and you have liquid iron coming out of the cell. The rest of the process to manufacture steel is exactly the same. So you go to a ladle metallurgy, correct the composition, go to a caster, and to the rolling mill, and you have your products as needed. Now, what I'm going to show you is the first step of our pilot cell. We are in the pilot stage at this point. Believe it or not, manufacturing steel in Boston. So if it's possible to believe, that's what it is. So I brought it so you can see. So that's green steel, no carbon involved to manufacture. Now, the big advantage of the process is that soup of oxides is composed of oxides that are more stable than the iron oxide, as I mentioned, and they are alumina, calcium, magnesia, silica, which, by the way, are the impurities in the iron ore. So, therefore, you can use any iron ore. You don't need to use, you don't need to work the iron ore or use very rich iron ores in the process. So, the same technology can be used to extract value from mining waste. So we are starting our first factory in Brazil, and we are going to extract niobium, tantalum, and tin from slags from the tin smelting. So cassiterite has columbite tantalite as a contaminant. After you process the cassiterite to take your tin, you end up with a waste. It's an environmental problem. So our process can get that negative cost material and transform into value for the industry. So in the age of efficiency, that's very, very important. And as you will remember, I mentioned the anode is made out of a chrome metal. So we are taking advantage of the fact that we need chrome for our cells and for our demonstration plants and eventually the industrial facilities we will build. So we are building our own plant to manufacture chrome metal, which will be the first one in the United States. So 100% of chrome metal is imported today. We will be the first chrome metal manufacturer in the States. Chrome metal is very important. There is no industry without chrome metal. So aircraft engines need nickel-based superalloys, oil and gas, energy, automotive, all the industry needs chrome metal, and 100% is imported. We are going to manufacture domestically very soon.
2 minutes.
So we are backed by a very enviable group of investors. We are very proud of having them all. Started 6 years ago with Breakthrough Energy Ventures, and we were able to build this syndicate of investors backing our journey. So thank you.
Thank you, Tadeo. I mean, just incredible, world-changing, maybe even world-saving sets of technology and processes. Well done, sir. We'll turn it now as a nice segue to Cooper.
How do you follow that? Okay,
How
I
do you
brought my
follow
own
that?
stopwatch.
I'm starting the stopwatch now.
We're ready. Hey, everybody. Nice to see you all. All right, going back to basics. Cement and steel are the literal foundation of our society. You probably all know this, but there's more anthropogenic mass on the planet now than biomass, and most of that is concrete. And there's a reason. There's a reason we use these Roman age materials, and that's because they are freaking amazing. They're cheap, they're everywhere. You can use a huge number of applications from them, and we've, most importantly, got hundreds of years, or in the case of steel, thousands of years of data about their properties. Of course, there's an issue with them as well, which is that they're responsible for massive amounts of emissions, but they also comprise trillion-dollar markets. And in both the case of cement and steel, unlike almost everything else we deal with in decarbonization, most of the emissions are from the process chemistry, meaning that if you decarbonize energy, you don't necessarily decarbonize steel or cement. And it's really fundamental to the chemistry. It makes them very recalcitrant to decarbonization. So what needs to be true for a low-carbon cement solution to actually matter? I would argue that you need to find a material that is absolutely trusted. The cost needs to be effectively equivalent. You need to deliver the same or better performance to conventional materials, and you need to be available at true scale, and I'm talking billion of ton per year scale. And that really boils down to, this is maybe a cynical view, but anything near term is probably an extension of the existing chemistry. Of course, there's much more opportunity in the long term for alternatives, which we'll talk about in a moment. And I'll just say from a venture perspective, we're looking for things that have return propositions, which means we're looking for, within the context of market boundary conditions, what actually provides for highly profitable unit economics as well. Make Mayor Pete's decision all that much easier. So when I think about the outlook for decarbonized cement, there's really 5 main ways to think about decarbonizing cement. The first, that's nearest term, it's already being implemented, is the extension. Cement actually is not the building material. Concrete's the building material, as you all know. Cement is the binder. So how can we use less cement per unit concrete? One thing we can do is supplementary cementitious materials like we use today. You can also think about strengthening the overall concrete mixture, so you need less cement per unit concrete. You can think about mixed design, so there's less space between chunks of aggregate in order for you to have necessary binder. In all these cases, we're talking about an extension of the existing ordinary Portland cement framework, and this is already being done to reduce the clinker factor. You can probably get to about 50%. Now today, under prescriptive standards, you can't in most parts of the world. But you can probably get to maybe 20 or 30%. And so there is an opportunity for regulators and for the Department of Transportation to really be a leader in pulling through innovation that can allow for the simple extension of the existing material system down to further reduction. Now, in the midterm, you can start thinking about reducing the emissions from the actual clinker itself, from OPC, and there's 2 main ways to think about doing that. The first is to deal with the energy associated with that, which is about 40% of the emissions. That will naturally come as we decarbonize the energy system. Maybe the last to fall, since cement uses the cheapest sources of energy today. Or maybe more novelly, you can think about actually changing the process itself to make ordinary Portland cement. Today we use limestone. That's the source of process emissions. The first thing we do is boil off CO2. What if we found a source of calcium that was scalable that didn't have CO2 in it? An example of a solution like that is a company called Brimstone, making the exact same material but just from a different feedstock. In the longer term, we can start thinking about alternative chemistries. And these have wild, potential ranges of benefit from a decarbonization perspective or a cost perspective or a performance perspective. And there's a few really interesting solutions that fall into those buckets. I think this is where we really need to start seeing the true pathway to starting with niche applications that are not necessarily structural. How do we start building the frameworks and the performance-based frameworks in order to be pulling through these solutions into the market over time? And then, of course, the thing we all measure ourselves against is CCS, which is someone else, I think Franz had it. It's basically a 200% premium if today you want to use CCS on a cement plant. So cement is the last to fall because of this. This is an interesting factoid you may not be aware of. Concrete is the lowest emissions material we make, and steel's not that far behind. So we just use so dang much of it. And so let's talk about steel now. Steel, that might be even harder to displace than cement. And the reason why is that metals are amazing. They're moldable and castable and weldable. They're strong, they're tough, etc. And steel is the undisputed king, and it's the undisputed king because of both performance, but really cost.
And it's responsible, like Tadeo said, for about 10% of greenhouse gas emissions, the majority of which are from the carbon that we're using to rip oxygen off of iron oxide. And so when we think about the outlook for decarbonized steel, in the near term, we can talk about decarbonizing some of the energy used in steel. There's been an electrification, secondary steel, but these are probably 10 to 20% kind of improvements along with efficiency. You can think about using alternative reducing agents. So instead of using carbon to rip the oxygen off, you could use like a hydrogen. That's discussed. Great solution. Today, 70% of all steel is blast furnace, 25% is recycled, and 5% is direct reduced iron with methane. You could think about replacing some of that methane with hydrogen. Hydrogen also costs more than methane, of course, but that's a potential solution in the near term. In the midterm, I won't belabor it because you just heard from Tadeo, but Boston Metal is a great example of a solution that follows the 3,000-year trajectory of reducing the cost of steel by improving the efficiency. And the only place to go from here today of thermochemistry is to move to electrochemistry, which is precisely what Boston Metal is doing. In the long term, we could consider alternative materials, but I'll tell you, steel is the lowest emissions, lowest energy, lowest of all the materials we make today. So anything you replace steel with is typically worse. Maybe biological materials or carbon-based materials could be an exception to that. But we should be open to thinking about alternative materials. And then CCS, of course, is a default option. So I'll close here by just thanking you for your interest and involvement here. There are some key needs we already talked about, which is, one, these are merchant markets, which means we need absolutely to have advanced procurement and offtake commitments in order to have a plant financing for any of the solutions, whether it's a Boston Metal plant or it's a Brimstone plant or whomever you like, any of the innovations that this panel is working on. We need to have clear paths to financing plants. We need to have opportunities to participate in any of the incentives that are coming through in the IRA and otherwise. And there needs to be clear standards and assistance in navigating the certification process. Thank you, Mo. But I'd like to leave you with a message of optimism, because there are real options, and there's a really strong pipeline of innovation, which I could not have told you 10 years ago. These are truly reasons for optimism. And I'll conclude by saying the DOT is truly critical. The government is the most important customer and standard bearer for infrastructure materials, and the DOT is the most important standard bearer within the government. So thank you for your interest and involvement. Let's go decarbonize some infrastructural materials.
Thank you, Cooper. While Maggie comes up, I'll just say, Cooper, thank you for engaging with us, this community. Thank you for clearly articulating the needs. I saw the slides, procurement and other things. And so thank you for that. Thank you for also for your continued engagement with this community. Now let's turn to Maggie to give us her perspective and deeper dive. Maggie?
Hi, good afternoon, everyone. And I guess I should say, Happy New Year. It's still New Year. So, well, here we go. We believe infrastructure creates opportunity for everyone, an uplifting community, improving access, sustaining our planet. Some of you might know our company. I really don't want to talk about it, but one thing I want to clarify, we don't just build tall building. We do airport and other infrastructure. Just happen. There's a few examples that we have. We have some past and current project that we're doing. And this is the slide that earlier the Secretary was talking about. The reason why I'm talking about this is we are doing 16,000 PSI, concrete mix design in high-rise building. And we have been collect data. And we know that if we can do high-rise, we could do something about infrastructure and roadway. And this is just a few things. And one of the things that we have done in high-rise and mixed design is we did replace cement with waste in landfill material like fly ash. So it works. Now, the other thing that we want to talk about it is embodied, important of the embodied carbon. We really can put the genie back to the bottle. As you guys can see, the operation carbon can be designed maintain, and upgrade out of the building, the embodied carbon in the construction material can never be recovered. It is front-loaded and already in the atmosphere. As you guys can see the example behind me, the blue is the embodied carbon. What we can do is the green. We can't go back. We only can go forward in the future. How can we reduce it? And that's up to us to help. And the grid line, which is on the straight line white, is a zero carbon grid. We can do it. It just matters how and when and where the money is. The other thing is, I'm an outgoing president for Concrete Industry Board, and we actually issued a green concrete guideline last year. And the cement pollutions, as of roughly, is about 8% in the global carbon emissions. CRB has been working to help reduce the carbon footprint of concrete. We have volunteer measures that designers and engineers are considered as a part of carbon footprint reduction strategy. We actually come up with a strategy to try to do this. So I'm just going to give a little bit of highlight for this really concrete guideline is. It's a roadmap. We want the highest concrete standard with zero extra cost. We want to use replacement material. We want to use the letter grade. As you guys can see on the other side, there's a letter grade from A to F. And there are the formulas that we could calculate the cement, we could calculate the strain, we could calculate the GWP and the EPD. Before I go to the example, I just want to remind myself, as everybody else, the cement manufacturing, the limestone, clay. As everybody knows, that we have to heat it 15,000 Celsius, equivalent to 2,732 Fahrenheit, pretty hot. And we're using forest field, and we come up with, like the panel said earlier, 1 ton of CO2 is for every ton of the cement. Can we do something about this? Like the steel, can we use electric faucet? That's a question that someone needs to help us out. Now the other one is, what is concrete? And mostly the ingredient combined and the mix in the plant on the truck. These are the typical formulas, as everybody knows, but we are only concentrate the cement to 10%. So right now, this is the example that we talked about earlier. We're using the 4,000 PSI mix. We use 50% Portland cement replacement, maintaining design for strain for 7 days, and we're using 28-day strain to come up with 72,000 PSI. So for the equation, which is the letter grade, on equation 1, the cement we rated A. Equation 2 with the strain, we rated B based on using 28 days break. For equation 3, which is GWP, is rated A. This actually happened. So for the conclusion, really, most concrete should be able to achieve a B rating in most cases, but the best mix for the environment may not be the best mix for the project. And thank you for the opportunity.
Thank you, Maggie. As we bring on our last speaker, Mo Jamshidi, I think, Maggie, you kind of start to get to performance characteristics, right? You have these new materials, but how do they perform? And so I think, Mo, that's certainly your sweet spot, so the floor is yours.
Okay, thanks. I'm going to go over my slides pretty quick, only 4 or 5 slides, and I want to thank everybody to hang in there with us this long, sitting there. Most of what I'm going to tell you for the practitioners in the room, it's really nothing new to you, but I just want to emphasize the role of the state DOTs in this whole transportation material business. All the DOTs want materials that are durable, easy to build, they're readily available, predictable, you can name it, repeatable. We can have a standard specification for them, we can get for what we want at a reasonable cost. And of course, we want it safe, not just for the time we're building it, but for years later than when we have to do maintenance on them. So what we need to work on is a little bit different, a little bit, I think, paradigm shift as far as the state DOTs is concerned. Historically, we've been spending on R&D funding on making the material we already have more durable, making sure they're more constructible, smoother, and so we can get our customers, the traveling public, what they want and make it last longer. The new component that we've added to this whole thing is now we have to make sure the same material that we create, from mining the aggregate all the way to going to the plant, going to the site, building the project, and maintaining it, that we have a lower carbon footprint. And I think that's the mind shift that we have to start working on in our research projects. We have to ask ourselves, and just being here this week, I'm really encouraged by all the work that's going on nationally to address just that. I know for a fact that Minnesota DOT, we have MnRoad, we have NIST, we have FHWA, they're all working in reducing the impact, the carbon footprint of cement by introducing different levels of limestone and other things that's going on in the asphalt arena, from just simple things to keep the aggregates dry so we don't have to heat them as much. These all will pay off because, as I said earlier, there is a huge amount of these materials we use, and every small little bit we do is going to make a big difference. One thing that I want to emphasize, and I want to say this on behalf of all the other DOTs, we don't like mandates. These materials and everything that are coming on board, it's all great, but mandates have shown over and over they don't work. I can give you an example for back in the days when we got the mandate to use crumb rubber, which is from old tires, into our asphalt, and we used it, and there was not enough research to know exactly how to do it, and then we paid for it. A lot of projects didn't go so well, so we use crumb rubber now, but after years of working on it, perfecting it, now it's working really well in all parts of the country. So transportation infrastructure, I want to emphasize, is not a dumping ground. It's not a place to put things that you don't want to put in the landfill. You have to engineer it to make sure it's lasting long enough so that we don't have to go back and replace it, because replacing it is not only bad for pocketbook, is really bad for the environment. So barriers to implementation. Secretary said it well. He did not like potholes, and neither do materials engineers, because they hear it from their mayors and their governors. So DOTs, state DOTs, want to make sure materials don't fail. They have a history of performance. They know what to count on. And we've had really good examples of the things that we wanted to do and it didn't work. In Nebraska, I can tell you the Class C fly ash that came in back in the 80s, just replace 25% of the cement with it, it'll be great. You got the strength you need. Well, later we found out that wasn't a very good design for us because of the ASR we had with the concrete. We needed a Class F fly ash, not the C that we have locally. We now use both of them, but we've engineered it to account for that. New England states, for example, had a terrible experience with using REOP engine bottom oils and acid modification in the earlier. They didn't even know those things were in the binder for the use of the asphalt. Well, manufacturers were doing it just to meet the performance tests in the lab for the super pave, and later we found out that they were using it the wrong way and lots of premature failures, and that wasn't any good. So we want to make sure when we bring new materials, we do our homework and we do it right. So how do you talk to your state DOT and get them excited about the new material you want to introduce? Work with them early. Don't wait until the product in your mind is all done and ready for prime time and then find out it's really not going to meet the state needs. Get them in early. We do not like normally proprietary items because we want to put the stuff for bid and we want to get competitive bid. And proprietary material is challenging for the DOTs to use. But if you work with the Committee on Materials and Pavement of AASHTO, we will create with you some performance-related specifications that you can put in place where all the DOTs can play from the same sheet of music and use your material as long as it performs the ways it's supposed to. So I've gone over lots of issues that you probably all know, and this has been fun. Thank you.
Thank you, Mo. Mo, thank you for kind of hitting cleanup here and really hitting it out of the park in the sense that, what does it really take for us to really move the needle here and get some of these new materials that perform and also have some climate-saving benefits? How do we get those moving? And so you really laid out, what's the reality of really getting those things implemented. At this point, I kind of want to move to close. I want to thank everyone who's here. I want to double down on the thanks and appreciation for Secretary Buttigieg and his participation. I learned that this is the first technical session that a Secretary of Transportation has participated in at TRB, and this is something that his leadership and the department's leadership, and honestly the whole U.S. government, is something we must move the needle towards net zero in the transportation sector in the same way, at the same time, maintaining the safety and performance standards that we all have come to rely on. And so with that, I just really want to thank everyone in this panelist. Please help me in thanking them, and thank you.